Hi, welcome to one and all. Next, we will be discussing on Ramanujan sum and generalizations. Before that, let us go through the previous section of Mobius functions, which you have learned already. The Mobius function mu of n is defined as follows: mu of 1 is 1, and if it is greater than 1, if n is greater than 1, then we can write n as a product of prime factors, and then mu of n is equal to minus 1 raised to n if a1 a2 etc ak are 1, and in all other cases mu of n is 0. That is, if the prime factors are having only exactly 1, then this mu of n is minus 1 raised to k, otherwise it is 0. So let us note that mu of n is equal to 0 if and only if n has a square factor greater than 1. So let us find out some uh, values for this Mobius function. For mu of 1 is 1, mu of 2 is minus 1 because mu of 2 there is only one prime factor, so it is minus 1. 3 is also minus only one factor, so minus 1. 4, it has two prime factors because 4 can be written as 2 raised to 2, so there are two prime factors, so it will become 0. And 5, there is only one prime factor, so minus 1. 6, there is two prime factors, but it's both the powers are of 1, that is minus 1 times minus 1, so that is why it is 1. And 7, it is minus 1. 8 is 2 cubed, so it is more than 1, so this becomes 0. 9 is also 3 square, so this is 0. And 10 is 5 times 2, so it is minus 1 times minus 1, so that is why it is 1. So one of the important property of Mobius function is based on the divisors, the divisor sum sigma d divides n mu of t. If you have already learned this result, that is, if n is greater than or equal to 1, then sigma d divides n mu of t is the greatest integer function 1 by n, which is equal to 1 if n is equal to 1 and 0 if n greater than or equal to 1. Now let us go to our section Ramanujan sum and generalizations. You have already studied, when you have studied Mobius functions, you have studied a result on Mobius function, that is the Mobius function uk is a sum of the primitive kth roots of unity. So this result can be written as sigma m mod k, GCD of mk is 1, e raised to 2 pi I m by k equal to mu of k. So what is actually Ramanujan sum? Now we will go to Ramanujan sum. It is nothing but the nth power of this primitive nth kth root of unity. So let us see what is the definition. It is, let n be a fixed positive integer and consider the sum of the nth powers of the primitive kth roots of unity. This sum is known as Ramanujan sum. N be a fixed number and the sum of the nth power of the primitive kth root of unity. So this is called the Ramanujan sum and is denoted by Ck of n. So what is Ck of n? Ck of n is nothing but summation m mod k, GCD of m and k is 1 and e raised to 2 pi I mn by k. So here additional term of the primitive kth roots of unity is only n. So if n is equal to 1, then it will reduce to the Mobius function. That is, the sum reduces to the Mobius function when n equal to 1. That is, mu of k is equal to Ck of 1. Now let us see one example related to this. Suppose I am considering the sixth roots of unity, and here I am considering the primitive sixth roots of unity. So we have already studied that here the primitive sixth root of unity are 2 pi I by 6 and e raised to 2 pi I 5 by 6. E raised to 2 pi I is by 6 and e raised to 2 pi I 5 by 6. These are the two primitive sixth roots of unity. So now mu of 6 is nothing but the sum of these two primitive roots, that is e raised to 2 pi I by 6 plus e raised to 2 pi I 5 by 6. How to find these primitive roots? They are the numbers which are relatively prime to 6. So that is 1 and 5. So mu of 6 is e raised to 2 pi I by 6 plus e raised to 2 pi I 5 by 6. So then what is the Ramanujan sum? Ramanujan sum C6n is nothing but the nth root of the primitive sixth root of unity, that is e raised to 2 pi I n by 6 plus e raised to 2 pi I 5n by 6. The next node will be that in this ck of n, if k divides n, then this will reduce to the Euler's phi function, the Euler-Torsion function, because we know that e raised to 2 pi I mn by k is 1 when k divides n, because this will reduce to an integer form, and this will reduce to 1. And in all other cases, if k does not divide n, then this part will become 0. So in that case, we will have ck of n will become summation k equal to 1 to n. Here those terms which are having only 1. So that means this 1 will be nothing but 5k. Now the third result which is given here, is ck of n is sigma d divides gcd of nk d mu of k by d. This we will be proving this result later, but we immediately we want to find some consequence of this result. That is when n equal to 1, you can see that ck of 1, that is when n equal to 1, this 1k, this will become d divides k and d mu of k by d. That is nothing but the Mobius function, that is mu of k, because sum of the devices sum is mu of k. That is why ck of 1 is mu of k. And uh, when k divides n, then we know that the GCD of n and k will become k, and in that case ck of n will become sigma d divides k d mu of k by d, which will become Euler torsion function phi k. So this is the result. What is the importance of this result is that this is the result which Ramanujan used to prove the certain theorems. So this is very important result that we will prove this result later on. Now let us consider the general sum of the form of this form. Ckn is sigma d divides nk d mu of k by d. So we are going to consider a general result of this, where we are replacing this d by f of t and this mu of k by d as g of k by d. This resembles the sum which you have already learned, sums for the Dirichlet convolution f star g. The only difference is that here we consider the sum d divides over nk, and earlier we had only d divides over k. So that is the only difference. So here d divides n and d divides k. That is the only difference here. So convolution that we sum over the sum subsets of the divisors of k, namely those d which also divides n. So that is the difference. Now let us recall what is Dirichlet convolution, which you have already learned. If f and g are two arithmetic functions, we define the Dirichlet product of Dirichlet convolution to be the arithmetical function h defined by the equation h of n equal to sigma d divides n f of d g of n by d. So let us see the speciality of this. We will be studying this in more detail later. Here we write f star g for h and f star g of n is for h of n. So now let us first show that this sk of n is equal to sigma d divides gcd of nk f of d g of k by d. We will prove that this function is periodic. We will prove first that this function is periodic. For that, let us find sk of n plus k. Sk of n plus k is nothing but sigma d divides n plus k k f of d g of k by d. But we know that nk plus 1k, this nk is gcd of nk is periodic function. So gcd of nk is periodic function, so we can replace this n plus k k as nk. So sigma d, this will reduce to sigma d divides nk f of d g of k by d, and this is nothing but sk of n. So we have seen that sk of n plus k is nothing but sk of n. So sk of n is a periodic function of n with period uh, with period k. Therefore, this function obviously has a finite Fourier expansion. Now let us see what is the finite Fourier expansion for this in our next theorem. Let sk of n equal to sigma d divides nk f of d g of k by d. Then sk of n has a finite Fourier expansion. Sk of n is equal to sigma m mod k ak m e raised to 2 pi I mn by k, and ak of m is equal to sigma d divides mk g of d f of k by d d by k. So this is what we have to prove. Now in theorem 8.4 we will immediately go to the proof of this, because it is very easy to prove, because we have already studied a similar result in our previous section in theorem 8.4. Let us go back to that theorem 8.4, what it is. So theorem 8.4, in 8.4 what we have studied is that f be an arithmetic function which is periodic mode k, then there is uniquely determined arithmetical function g also periodic mode k, such that f of n is equal to summation n equal to 0 to k minus 1 g of n e raised to 2 pi I mn by k. And from this we can find the value of g of n like this: 1 by k sigma m equal to 0 to k minus 1 f of n e raised to 2 minus 2 pi I mn by k. These two functions expressions can also be replaced by these two results. Here we can replace this as n mod k and m mod k. We can replace this as m mod k. So that is what we can use this theorem for proving the other result. So let us come to theorem 8.5. Now in 8.5 what we have to prove is, we have to prove that the skn has a finite Fourier expansion like this, as in equation 7, where ak of m is given as in equation 8. So we will prove this by using theorem 8. So in theorem 8 we can see that this ak of m has a Fourier series expansion of the form akm is equal to 1 by k sigma n mod k skn sk of n e raised to minus 2 pi I n m by k. So here we can now first apply the definition of sk of n. So if we substitute the definition of sk of n, that is sigma 1 by k sigma n equal to 1 to k sigma d divides n d divides k. This is nothing but d divides n gcd of n and k, and f of d g of k by d e raised to minus 2 pi I n m by k by definition of skn. Now we write n equal to cd. In this case, if we write n equal to cd and not for each d, the index c runs from 1 to k by d, and we obtain this result as because if we replace this n equal to cd, then we can see that this function will be replaced by this e raised to minus 2 pi. This n will be replaced by cd by n, and here when we remove this d divides n from here, then remaining part we will have sigma c equal to 1 to k by d, because when n is equal to c by d, then c is nothing but n by d, and here n will vary up to k because gcd of we have already taken d divides k, so the remaining is k by d, k by d. So c from c equal to 1 to k by d is this one, and now we replace d by this, we will get ak of m is equal to uh, what is given here in this form. And by theorem 1 we see that this will become 0 if d does not divide m, so in which case the sum has the value d. Hence we can say that akm is 1 by k sigma d divides k d divides m f of k by d g of d d, and thus we have proved the theorem, the result 8, and hence the result. Hope you have understood the result clearly. If you have any doubt, you can ask me by comments. Thank you.